Good morning, class. This is Mr. DeMarco back with another chemistry lesson. Today we're going to start the last topic of the year, which we call organic chemistry. This is our topic 12. And depending on how much time we have left, we'll determine how far we get in this topic. But the goal is to complete the whole thing. Organic chemistry is one of those topics where, with the reference table, and once you know how the system works, is a pretty easy topic to be successful in. But let's get into it. Here we have organic chemistry. Now, you might have heard organic chemistry in earth science. You definitely heard it in biology. And now we're going to get into detail in terms of chemistry. Organic chemistry is the study of carbon-containing compounds and their reactions. So the substance has to have carbon in it, or in a carbon-containing reaction for it to be considered organic chemistry. And for those of you that have taken bio, those remember all your proteins, your nucleic acids, your carbohydrates, your lipids, they all had carbon inside of them. And that's why carbon is a very important element for us in chemistry. But there's many chemical reasons why carbon is so important. First, let's take a look at the physical ones. Physically, carbon is on the right side of the periodic table, which means that it's a non-metallic element. Okay, in group 14, carbon is a non-metal. And because it's in group 14, we've learned that group 14 is a very special group on the periodic table because it allows the element to have 4 valence electrons. And we know that 4 is half of what the stable number 8 is, which allows carbon to make many different things. And carbon then physically is also what we say is allotropic. It can be found in many different forms. So carbon is very, very unique in the chemistry world. Now, translating that into chemical reactivity, we know chemically carbon, being in group 14, has the 4 valence electrons. Being halfway to 8, carbon can share, it can gain or lose electrons depending on what it's with to make a bond. Now, what this does for us in chemistry is it allows carbon to make multiple bonds. Okay, if you can think back to what our bonding topic was, some things had single bonds, but carbon could have a multiple bond. And if you're thinking, yes, there were some other elements that could also have multiple bonds, like oxygen sometimes, like nitrogen. But here we're focusing on carbon. Carbon can form multiple bonds. So if I pull 4 or 3 examples up here on the screen, I have 3 organic compounds. Now remember, how do I know it's organic? That's right, it has to have carbon. So all 3 of these things has carbon. And notice 2 of the examples not just have carbon, they also have hydrogen. That's going to be key in a little bit. And this compound over here not only has carbon and hydrogen, but it also has chlorine. So again, carbon can do a lot of different things based upon what it's with because of its 4 valence electrons and the ability to make 4 bonds. Now this number 4 becomes very, very important later on because we want to make sure our drawings are going to be drawn correctly. So if I pull up these 3 pictures, right, move my face out of the way, notice that in all 3 of these pictures, carbon has 4 bonds, right? In the structure down here, notice there's 4 sticks around the carbon. In the middle structure, there are 4 sticks around the carbon. Each carbon has 4. In this one over here, 4 sticks around the carbon. And we learned back in bonding that we can take our Lewis dot diagram and change those 2 dots for every one of these bonds. And that's why we would say CH4 has all single bonds, C2H2 has a triple bond, and C2H2Cl2 has a double bond. Again, when these things occur, we want full stability. So we have to make sure we have the octet rule for elements other than hydrogen, because hydrogen only needs 2. All right. So we're going to be able to, in this section, pull apart a lot of our organic compounds, knowing how to go from formulas to drawings, drawings to formulas, and then lastly, naming what all of these things are. Pretty easy to do once you know the process. Now, before we do that, I just mentioned that there are single, double, and triple bonds. Well, what becomes important in chemistry is on table P and Q, we can use this information to name things. Okay, so if I pull up table P for a second on your reference table, and if you don't have it, make sure you go grab it. Notice table P says organic prefixes, and it tells me if I have a set number of carbons, what the prefix of all of the things must be. So if I have one carbon only, it's a meth, 2 is eth, 3 is prop, so on and so forth. Okay, this is one of those charts where if you were taking the SAT 2 in chemistry, you would have to memorize all this information. Not hard to do once you understand how it works. The connection, though, is taking table P with number of carbons, and then how are the carbons drawn? That is table Q. And table Q is a very important chart because it shows me a picture. If I have a single bond, if I have a double bond, or a triple bond in between the carbons, that's going to affect the name and how many hydrogens that it can have. So notice in this first picture here, I have 6 hydrogens, but then I go to 4, and then I go to 2. And that makes sense because if carbon can only have 4 bonds, well, these are single, which means they have more room for other things. But once I put a double, less goes on the outside. And if I put a triple, even less goes on the outside. So again, this chart on table Q shows me what pictures are going to look like to get these different categories. And the other part I want to point out here is on table Q is this general formula thing. General formula will allow us to look at any formula of a hydrocarbon and determine what category it falls into. So all we do is plug in the N number, which is number of carbons. So let's say this one was 2 carbons. If I plug a 2 in, it's C2, which it is. And then 2 times 2 is 4 plus 2 is 6. There are 6 H's and there are 6 H's. So it tells me exactly what it is that I need. Now, here, all I'm doing is plugging in that information from table Q. If I have a single bond, single bonds from bonding are made up of 2 electrons. My ending of my compound is going to be ane. Double bond, it's going to be 4 electrons, and that's going to be an ene. And then triple bonds would be an ine. All right? So it's knowing how these things are set up and put together that give us the complete picture of an organic compound. And we'll see when we do some examples in a little bit. Now, the other part that we need to understand is that vocab words come in from solutions. And we say that if an alkane is present, that's a single bonded carbon structure, it's going to be saturated. Now remember, the connection of solutions. If a solution was saturated, that means it's full. So if I go back to table Q, notice my carbon, which can have 4 bonds, is totally full with 4 things. 1, 2, 3 H's and 1 C attached to this carbon. So saturated means full in organic chemistry as well. When we look at enes and ines, 4 electrons or 6 electrons, these things are unsaturated. Makes perfect sense. Its bonds are not completely filled with other elements, right? If I go back to table Q, notice carbon can have 4 bonds, and there are 4, but there's not 4 different things. There's only 2 H's and 1 C. Because it's a double bond, it can't hold anything else because it's being used in between that carbon. So there's only 3 things here. And then a triple bond, even different, right? Triple bond would be only 2 things can be held, right? So that's why it's unsaturated. So we're going to put all of this together in our examples once we know how it works. Now, as you saw on table Q, carbon loves hydrogen. And when this happy marriage occurs, we get a compound called a hydrocarbon. And this would be a famous question they ask on the Regents exam because it's an easy one. They'll say, which compound below is a hydrocarbon, or which one is not? And a hydrocarbon is exactly what the word means. It can only have carbon and hydrogen. So on table Q, notice it's only C and H, C and H, C and H. Easy to find. And if I know it's a hydrocarbon, I can draw it and write it in two ways. I can do what's called a condensed formula if I don't have a lot of space. But condensed formulas do give me some information, but not a complete picture. But I can draw that condensed formula into a structural formula. And for us as chemists, we like the structural formula better because structure tells us how the atoms are arranged, and that will give us a hint on its stability. All right, so let's put all this together and look at these three examples that I have. Now, this one says P, Q, and R. We're not using R yet, but we will in our next couple of lessons. So here I have three things. Now, first question, is these three items that I listed, are they organic? And the question is simple yes. How do I know? Three compounds, they all have carbon. Are they hydrocarbons? Pretty easy, right? Hydrocarbons have to have carbon and hydrogen. They all have carbon and hydrogen. Now, when I look at these things, I can draw what they are based on the category that they fit into, right? Now, notice this is C2H6. So 2 carbons. Well, if I go to table Q and plug the number 2 in here, I get C2. 2 times 2 is 4 plus 2 is 6. Bingo! C2H6 has to be an alkane. And is it? Yes, it is. If it's an alkane, I'm going to have 2 carbons. Each carbon has 4 bonds, 4 sticks, and that leaves room for my 6 H's. I know I did it right. C2H4, take the 2. If I plug it into table Q, that's C2, H, 2 times 2 is 4 plus 2 is 6. Nope, doesn't fit here. C2, H, 2 times 2 is 4, C2H4, bingo. That means the second one has to be an alkene. And then C2H2, same thing, doesn't fit here, but it fits here. Bingo, has to be an alkyne. So when I'm looking at my items, the first thing I want to be able to do is tell what category it fits into based on the general formula. If I know that, I'm halfway there because then I could plug in the other pieces. Notice that if these structures change from single to double to triple bonds, I lose saturation. Fully saturated, a little less unsaturated, even more unsaturated. But because these bonds are double and triple, I need to add one extra piece to my equation. Notice what it says on the bottom here. If a double or triple bond is used, it must get a number to tell its location. And this becomes important with functional groups with table R later on as well. When we're numbering carbons, we always want to make sure something special gets the lowest number. Now, in this first example, there's nothing special. So I can go 1, 2, or 1, 2. Either way works. Here, I have a double bond, which makes it special. Now, because there's only 2 carbons, I would call this the first carbon on either side because it's either 1 going this way or 1 going this way. Same here. But the number tells me what it is. When you're looking at ingredients of things that you use at home and you start to see numbers in them, that tells you it's an organic compound and it tells you where that special thing they're talking about actually falls on the compound. Again, I love organic chemistry because there's really no tricks. It's what you see is what you get. And we're going to see that as we go through. So let's take an example. I had C2H6 on the other slide, right? We know it's an alkane, but I could write it condensed as C2H6, or sometimes they'll make it easier for you and they'll actually write it out the way it's drawn, CH3 and CH3 together. These are both called condensed formulas. Notice this one, you have to check to make sure it's an alkane. This one kind of tells you it's an alkane just by looking at it. Because if I have two C's, the only way to get six H's would be with single bonds. So now what do I have here? I have two carbons. If I go back to table P, two carbons is F. So I know it's going to start off with an F. In between the carbons, I have a single bond. Table Q tells me if I have a single bond between the carbons, it's going to be an alkane. So this C2H6 structure has to be F-ane. F for two carbons, ane for single. Pretty easy to do. Take a look at this one. Here I have C5H12, or if I wanted to condense it the way I draw it, well, we say CH3, CH2, 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 CH3. Notice the way it's written is the way it's drawn. CH3, CH2, 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 CH3. They both are C5H12. Notice 5 gave me 12. That's why on table Q, 5 would give me 12. It's going to be an ane. But if we do the process, first thing is 5 carbons. 5 carbons on table P is pent. All single bonds. Single bonds are characteristic from table Q of alkanes. So this thing, or the condensed formula C5H12, that would be called pentane. Again, easy to do because you have your reference table and you know carbon can only have 4 bonds. All right, so let's do one last example together. Here I have C3H6 or CH2, CH2, CH3. Notice how it's drawn, CH2, CH2. Ooh, that should be CH2, CH, oops, and then CH3. So we got to take that 2 out. Okay, so let me just take that 2 out. There we go. And now we're all set. So if I have here CH2, CH, CH3, I have here a compound that has 3 carbons. Notice if I come over here, 3 is prop, right? 3 is prop. And then I have a double bond, and this is the first double bond, so I know it's going to be an ene, right? Because ene gives me a double bond, and that means it's going to plug into this formula CnH2n. So if I go back and I see CnH2n, notice 3 times 2 is 6. So I have here 3 carbons, and now here, if I number them, I get different numbers. This would be carbon 1. This is carbon 2. And this is carbon 3, right? If I number from this direction, that's carbon 1, that's carbon 2, and that's carbon 3. Notice I would have to number it from left to right because it gives this carbon the lowest number. If I went this way, this would be a 2, and 1 is smaller than 2. So that's where this comes into play. So we have to understand that this is going to be a prop, 3 carbons. It's going to have a double bond in it, so it's an ene. And because it's a double bond, I need to have a number. So that carbon-carbon double bond is between the first and second carbon. So the number, which has to be the smallest number, tells me where that bond goes. So this is a picture of what we say 1-propene. Now, I know what you're thinking. If I had the double bond here, does the name change? And it doesn't, because then I would number it from right to left to give it the smallest number. So that's 1-propene. Again, these take a little bit more time because of the extra piece of counting the carbons in the right direction. Again, you may want to watch that one more time before you move on. All right, so now let's take a look at this one here. We have C5H8. Where is my writing instruments? No. So let me come here. All right, so back in action here. So here we have a C5H8 compound. And when we look at the C5H8 compound, notice C5H8, right? 5 times 2 plus 2 is 12, so it's not an ane. 5 times 2 is 10, not an ene. 5 times 2 minus 2, well, that has to be a alkyne. So I gave you one of each example. So C5H8 is an ine. Now notice if I write it out the way I draw it, CH3, CH2, C, C, CH3, I get exactly what I need. Now notice it's a triple bond here. So the first thing is I have 5 carbons going across. So we know it's a pent. It has a triple bond in between the carbons, so I know it's an ine. Triple bonds have to get the lowest number. So now we have to think, how do I number this compound? 1, 2, 3, 4, 5. That makes this number a 3. Or if I go this way, it's 1, 2, 3, 4, 5. It makes this a 2. Because it has the smallest number needed, it has to be numbered from right to left. So this, correctly named, would be a 2-pentyne. The reason why it's 2 is because if I go right to left, I get a small number of 2 for this carbon where it starts. If I did it incorrectly and said 1, 2, 3, I give it a high number, which is incorrect. Now, again, on the state exam, they love a question like this because they'll say, which choice below fits the structural formula the best? And they're going to have 2-pentyne, which is the answer, but they're also going to have 3-pentyne, which is not the answer, and then other things that don't make any sense. All right, so now that we went through the lesson, you'll have a worksheet where I'm going to have you draw some and name some structures that are pretty easy to do. All right, so if you need to watch it again, go ahead and watch it. If not, go right to work. Take care.